In this video, I'm going to show you the key differences between various waveforms. We have 4 oscillators, each set to 261.63 Hz, which in musical terms equals middle C. The first oscillator produces a sine wave, the next one a triangle wave, then the next one a saw wave, and the last one a square wave. Let's compare them. Sine waves are smooth and rounded, representing a pure sound with no overtones. The voltage goes up and down in a steady, predictable way, creating a clean, simple sound. The sine wave here in red color produces a single peak. As you remember from the previous lesson, this is called the fundamental frequency. The unique thing about the sine wave is that it's the purest of all waves, it doesn't really exist in nature, and in theory, it only contains one fundamental frequency with no overtones. So let's listen to the sound of the sine wave at this particular frequency. You can hear the sound can be described as very pure and a bit hollow. Now let's move on. Triangle waves are similar, but with sharper peaks, and they produce a sound that's still smooth, but with more harmonics than the sine wave. As you remember from the previous lesson, apart from the fundamental frequency, most waveforms also have overtones, which you can see here. The overtones of the triangle wave are odd numbers. What does this mean? For example, if the fundamental frequency of a triangle wave is 100 Hz, the partials will peak at 300, 500, 700 Hz, and so on. You can see the amplitude or the strength of these partials decreases over time. It's like a sine wave, but with sharp edges, and so it has overtones. The sound is similar to the sine wave, but sharper, and it's good for creating, for example, bell sounds. Now let's have a look at the square wave. Square waves have a distinct on and off pattern, creating a more hollow sound. The voltage quickly switches between two levels, which is why these waveforms are again rich in harmonics. Here we also only have odd harmonics, but the difference between the square wave and the triangle wave is that the partials on the square wave decrease slower as the frequency increases than the partials on the triangle wave. You don't have to worry about these details. You can always explore it later using the handbook. Square waves are good for bass lines and leads and clock signals, which we'll talk about later. The square wave sounds quite hollow, as you can hear. So again, the triangle wave in yellow in comparison to the square wave. You can see the overtones on the square wave in blue peak at the same odd frequencies as the overtones of the triangle wave, marked in yellow. So that was the square wave. And the last waveform we will look at is the Sawtooth Wave, also known as saw wave, shown here in green. Saw waves ramp up and drop sharply, creating a very complex and rich sound full of harmonics. The voltage goes up gradually and then suddenly drops, giving Sawtooth Wave the distinct cutting edge. This is the richest waveform, and it contains both odd and even harmonics. So in fact, you can say the saw wave is the only waveform also containing even harmonics. The result is a bright, buzzy sound, and it's good for creating sounds that resemble brass or string instruments. Let's compare the triangle wave, or for more contrast, and the square wave with only its odd harmonics, and the green saw wave with odd overlapping, and even harmonics. And here again, only the triangle wave and the square waveforms. So that's the main differences between these four waveform types. The key things to remember are the sine wave is very pure, no overtones. The triangle and the square waves only contain odd harmonics, and the saw wave sounds very rich, containing both odd and even harmonics. Understanding the shapes of these waveforms will help you predict and control how they will sound in your music.